So in the first homework, we tried to do something relatively simple. We wanted to ask you to design some sort of OTA that had these specifications. The biggest difference between these specifications and what you might normally be used to is the power consumption was meant to be extremely low. We encourage you to use the GM over ID design methodology that we introduced in lecture 1. The specifications hinted that it would be a two-stage amplifier. So, basically just due to the phase margin requirement. So what we ended up deciding to do is going to a two-stage amplifier. We used a NMOS input, PMOS active load, and then went to a PMOS load for the, excuse me, for the second stage here. This just makes the biasing quite simple. We didn't, specify that you needed to use, real transistors for your current mirrors. So that was a fine specification. And then within the design, we, start with the GM over ID design methodology. We added a second stage. We also biased this with about 100 nanoamps. So 100 nanoamps, for both stages. So that's 200 nanoamps total at a 1.2 volt supply that satisfies the less than 250 nanowatt total power consumption. And the size of this transistor is chosen according to the GM over ID design methodology to hit an additional 20 dB of gain. So you have 40 dB from the first stage and 20 dB from the second stage. For stability reasons, we added, the Miller compensation and, did appropriate calculations. These are kind of outlined here in terms of how we arrived at the values to get this. But one thing that happened when you do Miller compensation is that the bandwidth of that first stage decreases below the specification for what we're interested in. And so one trick to help improve that, which is especially useful for low power systems, is to use a DT-MOS technique, which is something we introduced in the first lecture there. And so here what we did is we actually connected the inputs to both the gate and to the bulk of the transistor. Now, of course, you have to be careful about this because you need to restrict your input common mode range in order to make this work and not turn on any diodes on the body of the devices here. But if you are careful about that, then what this effectively does is buy you 50% more transconductance for no increase in current. And so that helps improve the effective amount of transconductance, giving ultimately the same bandwidth that we're looking for. So here you can see we got our 60 dB of gain, about 2 kilohertz of bandwidth, and the noise happened to be okay as well. Now, we actually didn't talk about noise in lecture 1, and in fact, we won't even talk about noise today, but we will do a slightly more detailed treatment of noise in subthreshold in lecture 3. So please keep your eyes open for that. Okay, let's see. There was a question on the chat. Could we save some power if we use cascodes instead of a second stage? Possibly, yeah. If you can squeeze out 60 dB of gain in your first stage, it might have been able to reach there. There's many possible other solutions you could get here. So yeah, I think that would be certainly something to explore. Another thing that one could explore is doing a current reuse architecture where you have both NMOS and PMOS inputs. That complicates the biasing a little bit. Of course, if you then add cascodes on this, that requires a lot of headroom for all of your transistors. But remember, the benefit of being in subthreshold is that your transistors only require about 100 millivolts over them. And so you can actually stack quite a few transistors here, even with a relatively low supply voltage. Now, one thing we will learn, not today, but in lecture 3, is that sometimes it's actually more optimal to have only your input pair biased in subthreshold and your other transistors biased in above threshold, actually for noise reasons. So we'll get into those discussions in lecture 3.